Hello. In this third video on statistics, we're going to be talking about the standard error of the mean. In the last video, we noticed that when the sample size of our sample of salaries was small, the difference between the true mean and the sample mean was tended to be larger than each time we drew a sample. We got differences of around like $10,000 or more pretty frequently. But when we had samples of about 200 salaries, the difference between the sample mean and the true mean tended to be pretty small. It's hard to judge visually here, but it's maybe only a couple $1,000s on, each time we draw a sample. So each time, we can ask the question, how noisy is our estimate? If our sample mean is supposed to be an estimate of the true mean, then the difference between them is our error. And we might be interested in the average size of our error each time we draw a sample. And that average error is called the standard error of the mean. This is a special type of standard deviation. A standard deviation is the average difference between two quantities, two random quantities. So if we ask what the standard deviation, the average difference between the sample mean and the true mean is, that standard deviation is called the standard error of the mean. And I want to emphasize that it is different than asking what is the standard deviation of this histogram. The standard deviation of this histogram is saying, on average, how much does an individual's salary differ from the average salary? We're instead interested in what is the average difference between the average salary from our sample and the true mean. So one way that we could kind of visualize this question of ours, what is the standard error of the mean, is by collecting many samples, calculating the average salary from each sample, and visualizing that relative to the true mean. So again, here I'm just defining another plotting function. If we go ahead and run that, here on the x-axis I have the difference between the sample mean and the true mean. When the samples, and I've collected 1,000 samples. No, not 1,000 samples. I've collected 300 samples. So I've collected 300 samples here, and at the moment my sample size is 10. So remember, when our sample size was 10, the error between the sample mean and the true mean tended to be pretty large, around $10,000 or more. And what we see here bears that out. Many times, many of our samples have an error of approximately 0. But we see a substantial bulk of our histogram has errors ranging from negative $20,000 to positive $20,000. If we increase the sample size to say 200 where we were before, now many of our samples have an error still of about 0, and most of our samples have an error only of more, plus or minus $5,000. So when our sampling size is 200 instead of 10, our errors tend to be much smaller. Instead of ranging from plus or minus $20,000, they're now plus or minus $5,000 on average. I could push this even higher, up to 500. And when this is finished updating, we see this gets even, the scale here gets even smaller. Most of the errors lie between, say, plus or minus $3,000 in this case. And again, this is kind of the law of large numbers at work. As our sample size increases, we get a better estimate of the true mean. The error in our estimate tends to decrease. Now, there's another part of this graph that I have not been talking about yet, which is this black dashed line, which I have labeled the central limit theorem. In the language of statistics, this law of large numbers is formalized by the central limit theorem. It is a provable mathematical statement, that's what a theorem is, about the tendency of our estimate of the mean, that is our sample mean, to tend towards the true mean. And the central limit theorem not only tells us that we get a better and better estimate as our sample size increases, but it tells us what the standard error, what the average error we should expect between the sample mean and the true mean is as a function of sample size. So it tells us how narrow this histogram should be. How wide should it be? How spread out should it be? And we can see, for a sample size of 500, this histogram is spread more or less from -3 to 3, with a little bit of a tail out to about -6 to +6. On the other hand, if we bring this way back down to 10, the central limit theorem tells us, this black dashed line, that our histogram is going to be spread out mostly from about plus or minus 25, but even out to about plus or minus 50. So it actually tells us, the central limit tells us what distribution of sample means we should expect. And the larger our sample size, the better the central limit theorem describes what we'll see. So not only does the central limit theorem tell us that we get a better estimate of the mean as we increase our sample size, but also the central limit theorem tells us what the average error between our sample mean and the true mean should be, and that standard error, that estimate of the standard error that we would get from the central limit theorem gets better and better itself as the sample size increases. And we can see that a little bit if we bring this sample size down to 10. We see the histogram is a little bit skewed from the central limit theorem. even when I run this cell multiple times and pick out multiple sample or do the whole sampling process multiple times, we see the histogram is often peaked a little bit to the left of where the central limit theorem says it should be. But when we increase our sample size up to about up to 500, when I run this again and again, oh right, if I actually set this to be 500 here, then when I run this again and again, we see each time with a sample size of 500, the histogram much better matches that black dashed curve than it did when the sample size was 10. It's no longer skewed off to the left. So, to bring in some formal mathematical notation, the central limit theorem tells us that as the sample size increases, the sample mean tends to follow a normal distribution. That's this bell-shaped curve, the normal distribution. You've probably seen this before. So the central limit tells us that the sample mean itself is distributed following a normal distribution with this standard deviation. So the standard deviation of the sample mean, which we call the standard error, equals the square root of the variance, the square of the standard deviation, the variance of the distribution of salaries, that's this black dashed curve, the distribution of salaries. So the variance of that distribution divided by the sample size square root. As the sample size increases, the standard error will decrease, because as this gets larger in the denominator, this whole quantity gets smaller. So this is a little bit tricky to think through, because we're now talking about two different distributions. One, we have a distribution of salaries. That distribution is a probability distribution describing the likelihood that we pick out a particular salary for an individual in our sample. From this, once we collect a sample, we can calculate the sample mean. The individuals in our sample, their salaries are random. They are random variables. Since the sample mean is calculated from this collection of random variables, the sample mean is itself a random variable. And since it's a random variable, it follows a probability distribution. The central limit theorem tells us that the probability distribution that describes the sample mean is a normal distribution. And it will have a mean, it's centered around the true mean. And the standard deviation is given by this quantity. I realize that this concept is difficult to pick up for many students, and it sometimes helps to have multiple explanations from different people for any particular idea. So I am going to share if you would like other explanations of the central limit theorem and the sampling distribution of the sample mean, check out the videos here. So I will add this link, I guess, to the video links in the schedule. I'll just add it as like link to the a statistics playlist, in case you want that as a supplement. Or if you want to just copy it out from here, that's fine too, but that's probably not convenient for most people. So we have arrived at another exercise, which I will create another question for on the discussion board. So you can see I'm waiting until I post these lectures before I actually submit the question. So DS Intro Statistics Exercise 2, Exercise 1. Difference, or standard deviation versus standard error of the mean. Oops. We want to do that here. There we go. So I'm going to now conclude this video about standard error. And I would like for you to, either having watched this video or perhaps having taken a break from these lectures to consult the videos on this playlist, which cover a variety of statistical topics, including what we've just discussed, including going into more depth on the central limit theorem, and then on to hypothesis testing and confidence intervals. So, having watched this video and as many of these playlists or as many videos on this playlist as you like, whenever you feel comfortable, I'd like for you to go to the message board and participate in that question for this exercise. In the next video, we will be using what we've learned about estimating the mean and estimating its error to perform some hypothesis testing.